You know, when it's loaded, of course, now it can spin. Can it spin? Why can't it spin? It was spinning. Now it is not spinning. What they set up then with this thing is that how do they physically read it? Well, they've got a laser, okay, and the laser reads, and it's comparing this distance to this distance, right? And specifically, if there's a pit there, the difference, if this is D, if that's the depth of the pit, right? The laser that goes down into this thing and then back out, its path length difference compared to this is 2D, right? And if you set up 2D, if that's equal to half a wavelength, well, gee, with waves and sound, that relationship, what that means is that you're going from constructive to destructive, right? So what the laser does is it compares the beam that shines off of this to the beam that shines off of that, and if this is dark as opposed to light or something like that, then it's a bit, right? They simply have a little electric eye that reads the intensity of the light and reads on or off with that. Yeah?
That makes sense, like how the pitch would vary, but how does like something like timbre get recorded?
Oh yeah, timbre. Well, that's all in the waveform. That's like steady acoustics or something like that. But it's Fourier transforms and all of that, right? So this the notion that it's not a pure sine wave, right? That it's I don't know if you did the oscilloscope lab and just sang different tones into it, but you could see if you went doo, it was this, and if you did doo, it was something crazy, right?
Wait, like what?
Doo. So that's one of the examples on your sheet. If the pits are 150 nanometers deep, right? It's on the note guide from last time. What wavelength of laser light will create destructive interference relative to this depth? Well, G, if 2D is half the wavelength, and that's D, right? Well, then twice 100, and this is not exactly rocket surgery, okay? So if twice 150, the skill set, though, apparently was rocket surgery, okay? And people, deeply didn't know how to do, binding energy or something like that, So you guys won't let me down, though. Okay, so gee, what does lambda have to be? Well, if 300 is half the wavelength and the wavelength is 600 nanometers. Yeah? Huh? Yeah, that's reddish light, right? Because 700 is like deep red and 400 is like ultra or violet colored. Yeah?
So when you burn a CD,
yeah.
Does it change the grooves that are...
Yeah, it's digging pits into the CD, right? It's drilling little holes in there that the other lasers can read, okay. Right? So apparently it must have, I don't know if it has two lasers or if it just takes the same laser and ramps it up a bit, right? Because obviously you don't want to read with that same laser, right? It's like bad laser. Yeah. I have no earthly idea, right? It could be that they can erase the pits somehow and fill them in. I don't know.
I think it has something to do with remelting.
Remelts them and they fill in. Yeah. This doesn't sound like something you could do very many times. How many times can you do it?
I don't know.
Yeah.
So then how does solid state work as far as representing data?
Oh, they've got these little gates that can retain the value, right? So like RAM, they've got a system of transistors or whatever. They're clever that when you turn it on, they just sit there and go, okay, I'm on, right? And then you can actually send another signal in, and it'll flip the other way, right? You'll get to that when you. But it's not trivial. 1 bit is like many transistors. Yeah.
So once a CD player reads the grooves on the CD, does
Uh-huh.
that have to be translated into speaker?
Okay. Yeah. Hold on. Right. Okay. So blah blah blah. Okay. The second thing that they want you to do, second type of problem that they want you to do associated with this is this notion of resolution, because that little laser that's looking at that CD is like a little telescope looking at stars in the sky, only it's not really. But and so there's something called the Rayleigh criterion, which I think you guys did last year, right? Yeah, slightly. We didn't spend a lot of time on it. But the notion is this, that the larger the lens is for your telescope, or the larger the aperture of your telescope, the better you're able to resolve the distant objects, right? So a small a small theta means that you can resolve very small angles, right? Okay, and so this is the criterion, and the criterion just places an ordinary aperture makes an interference pattern of bright, dark, not very bright, dark, even not brighter thing, dark type thing, right? And all this does is it places one star's maximum at the other star's minimum, right? So it's this arbitrary thing that apparently Raleigh came up with, right? And the way it pertains to a DVD is that you could draw this little picture here. Here is the little lens, right? The lens is B in diameter. Why they picked B, I really don't know, but I'm not going to change it to something else because that's what's in the data packet, right? Okay. There's the B. Here is this, this disc going by, and here's a couple pits here, right? And I got to look at this. R is the minimum distance separating these pits. So R is probably this distance here. Yeah? Okay. D is this distance here. And so basically this is the angle that we're trying to represent. There's our theta, right? And you guys know that theta is just R over D. Only this should be R and that should be D, but I'm not going to go there. Okay? Yeah? So if that's D, right, like that. And so this relationship just says that theta, which is equal to the distance between the pits, like that, is equal to 1.22 times lambda over B, right? So if you look at this, two ways to increase your resolution. Either get a bigger lens, right? Okay, spend more money for the lens. And the lens of that thing, I don't know if you looked at it, was kind of big, wasn't it? The lens that focused that laser was kind of big, surprisingly big, right? That's to give it better resolution, okay? Or you can, what can you do? What can you do with wavelength to make this smaller? Decrease the wavelength, right? Decreasing the wavelength means that you might go from, I don't know, red or infrared to, I don't know, blue. Would that be what Blu-ray is about? Is that why Blu-ray lasers use blue light, which is a short wavelength, so they have a better resolving power? It might be. Could that be why all the time Netflix DVDs wouldn't read in my DVD player, but my Blu-ray player has yet to reject one?
Quite possibly.
Yeah, it's got a better laser in it. It's better at resolving. It also probably has more processing power, more ability to correct for errors, because it's later software. It's probably more to do with it than the blue color of the light. Okay. And then we were going to, this is the answer to David's question. How do they represent the bits on the disk? It would be very cool if it was as simple as like a 1 bit is off and this is a 0 and that's a 1 or something like that, for example, right? It's not quite that simple. What they have are actually, it's more like a barcode. It's a protocol sort of like a barcode where they've got different lengths of things, and I can't remember how many different lengths they have, right? But they've got different lengths of these things, and it's like a barcode. They're representing, they actually use 14 of those things to represent 8 bits. And the reason for that is that it's more robust. And somebody wrote this very neat, I think in Wikipedia, on how it works, and I understood it, and I forgot it because I don't really use that too much. But it's, suffice it to say, you could look it up and learn it in a half hour from some engineering book. Yeah?
So I guess that makes sense why then if you like scratch a CD, but why then if you like smudge a CD or like put your hand on it and move hand, why does it stop looking at that?
Oh, smudges. Well, basically what you want to avoid, the worst thing on a CD are grooves that go parallel with these grooves, right? Because that takes out like so many bits that it can't figure it out. Smudges, I don't know. Maybe smudges are bigger than scratches. I don't know.
You just can't read it.
The thing it doesn't mind, by the way, is a scratch this way across it, right? Because it's like those bits that will drop out, but it can actually, there's error correction stuff that can fill in those bits, right? Especially on DVDs. DVDs have far more error correction than CDs because they have to, right? CDs are not actually all that robust.
So if you scratched it like coming out from the center, it wouldn't...
Not so bad. That's not as bad as scratching it along, Radial scratches are not so bad, but scratches, tangential scratches are bad, yeah. And then we were going to do some whiteboards on this, but that's not very hard. Look how fast you're learning.
Whoa, look at us.
Ooh. Okay. So let's do, I don't know, yeah, we're running out of time. Let's do this example, and then we got to do our...
Question.
Okay, so DVDs have pits that are about 0.7